today's class. So today at first we are going to solve this numerical. So let f of x equal to x log a minus a log x if x greater than a greater or equal to e. So f of x is continuous if x greater than a greater or equal to e. Now f dash of x equal to log a minus a by x, and this is greater than 0 because a greater or equal to e and a by x is less than 1. So f of x is strictly increasing. So f of x greater than f of a and f of a equal to 0 if x greater than a greater or equal to e. So this implies x log a minus a log x greater than 0. This implies x log a greater than a log x. So this implies log a to the power x greater than log x to the power a. So this implies a to the power x greater than x to the power a if x greater than a greater or equal to e. Hence, proved. Now we are going to solve this numerical. So let f of x equal to sin x by x for all x belonging to closed interval 0, pi by 2 and f of 0 equal to 1. So, f of x is continuous in closed interval 0, pi by 2. Now, f dash of x equal to x cos x minus sin x by x squared. So, for 0 less or equal to x less or equal to pi by 2, what we can say? Yes, x squared greater than 0. Now we are going to choose another function phi of x, which is equal to x cos x minus sin x for all x belonging to closed interval 0, pi by 2. Now phi dash of x equal to cos x minus x sin x minus cos x equal to minus x sin x for all x belonging to 0, pi by 2. And this is less than 0. So, phi of x is, monotonically decreasing for all x belonging to closed interval 0, pi by 2. So, for 0 less or equal to x less or equal to pi by 2, phi of x less than phi of 0, that is x cos x minus sin x less than 0. Thus, f of x is monotonically decreasing. Or you can add here x cos x minus sin x by x squared less than 0 because x squared greater than 0. That is f dash of x less than 0 for all x belonging to open interval 0, pi by 2. So this is monotonically decreasing for all x belonging to closed interval 0, pi by 2. So for 0 less or equal to x less or equal to pi by 2, f of pi by 2 less or equal to f of x less or equal to f of 0. So this implies 2 by pi less or equal to sin x by x less or equal to 1. This implies 2x by pi less or equal to sin x less or equal to x when 0 less or equal to x less or equal to pi by 2. Hence, proved. Now we are going to solve this numerical. So at first we are going to choose f of x equal to a0 plus a0x plus a1 x squared by 2 plus a2 x cubed by 3 plus plus an x to the power n plus 1 by n plus 1 for all x belonging to closed interval 0, 1. Now since f of x is a polynomial, it is continuous in closed interval 0, 1. Again, f dash of x equal to a0 plus a1x plus a2x squared plus plus an x to the power n for all x belonging to 0, 1. So, f dash x exists in open interval 0, 1. Again, f of 0 equal to 0 and from construction f of 1 equal to a0 plus a1 by 2 plus a2 by 3 plus plus an by n plus 1 equal to 0. So, f of 0 equal to f of 1. Since f satisfies all the conditions of which theorem? Yes, Rolle's theorem. What we can say? We can say that there exists a point, say C in open interval 0, 1 such that f dash of C equal to 0. So this implies a0 plus a1c plus a2c squared plus plus an c to the power n equal to 0. Thus, the equation has at least, or it is better to write the given equation has at least one root between 0 and 1. Now for solving this numerical, we are going to choose that A belongs to R, B, R beta D. Now, mod of f of x minus f of y less or equal to x minus y whole square implies minus x minus y whole square less or equal to f of x minus f of y less or equal to x minus y whole square. Now we are going to choose x equal to a plus h and y equal to a. Then minus h squared less or equal to f of a plus h minus f of a less or equal to h squared. Now if h greater than 0, then minus h less or equal to f of a plus h minus f of a less or equal to h. And if h less than 0, then h less or equal to f of a plus h minus f of a by h less or equal to minus h. Now by sandwich theorem, what we can write? We can write that left hand limit of f dash of 0 equal to right hand limit of f dash of not 0, this is a. So this is equal to 0. This implies f dash of a equal to 0. Since a is arbitrary, it follows that f dash of x equal to 0. That is, f is constant. Now we are going to solve this numerical. So at first we are going to choose f of x equal to e to the power x sin x plus 1. Now let a and b be two real roots of the equation e to the power x sin x plus 1 equal to 0 and a less than b. So f of x is continuous in closed interval a comma b comma derivable in open interval a comma b. Also, since a and b are two real roots of the equation, f of a equal to f of b equal to 0. So since f satisfies all the conditions of Rolle's theorem, what we can write? We can say that there exists a point, say C, in open interval a comma b such that f dash of c equal to 0. So this implies e to the power c sin c plus e to the power c cos c equal to 0. This implies e to the power c sin c plus cos c equal to 0. As e to the power c not equal to 0, sin c plus cos c equal to 0, this implies tan c plus 1 equal to 0. So, c is a root of the equation tan x plus 1 equal to 0, where a less than c less than b. Now we are going to solve this numerical. So clearly we can say that f of x is continuous in closed interval 0, pi by 2, derivable in open interval 0, pi by 2. Also, f of alpha equal to, so if we put alpha in place of x, these two rows will be same. So the determinant will be equal to 0. And if we put beta in place of x, these two rows will be same. So the determinant will be again, yes, 0. So since f satisfies all the conditions of, yes, Rolle's theorem, what we can say? We can say that there exists a point, say C, belonging to open interval 0, pi by 2, such that f dash of C equal to 0. Hence, proved. Now we are going to solve this numerical. So since it is given that f dash of x exists in closed interval 0, 1, we can easily say that f of x is continuous in closed interval 0, 1. Now let g of x equal to x squared for all x belonging to closed interval 0, 1. Then g of x is continuous in closed interval 0, 1, and g dash of x equal to 2x, which is not equal to 0 for all x belonging to open interval 0, 1. So, by Cauchy's mean value theorem, what we have? We have f of 1 minus f of 0 by g of 1 minus g of 0 is equal to f dash of we have a point, say C, in open interval 0, 1 such that this by g dash of C. So this implies f of 1 minus f of 0 by 1 minus 0 equal to f dash of C by 2C. So this implies f of 1 minus f of 0 equal to f dash of C by 2C. So, f of 1 minus f of 0 equal to f dash of x by 2x has at least one solution in open interval 0, 1. Now we are going to solve this numerical. So here it is given that f of x equal to mod x, and we can easily say that f of x equal to mod x is continuous in closed interval minus 1, 1. Again, f of minus 1 equal to f of 1. Now, f dash of x equal to 1 if 0 less than x less than 1 equal to minus 1 if minus 1 less than x less than 0. Now, right hand limit of f dash of 0 equal to limit h tending to 0 plus f of h minus f of 0 by h equal to limit h tending to 0 plus mod h minus 0 by h equal to limit h tending to 0 plus h by h equal to 1, and left hand limit of f dash of 0 equal to limit h tending to 0 minus f of h minus f of 0 by h, and this is equal to h tending to 0 minus mod h minus 0 by h. Since it is tending to That means h is tending to 0 minus mod h will be equal to minus h minus by h equal to minus 1. So, f of x is not derivable at x equal to 0. That is, f dash of x or f of x is not derivable in open interval minus 1 comma 1. Thus, Rolle's theorem is not applicable to f of x equal to mod x in closed interval minus 1 comma 1. So that's it for today. We are going to meet in the next class. Till then, bye.